Lesson 80, loudness. We will discuss how loudness changes for sound. So when we talk about sound, one of the key things we talk about whenever we talk about sound is volume or loudness. When we say, hey, that speaker is way too loud, that's one of the ways that we talk about sound. It's one of the ways that we can use to measure sound, is you can say, well, which is louder than the other one. And loudness is also really, of course, one of the first things that we learn how to measure sound, because you guys all know, how when something is louder than something else. The problem with loudness is units. Now, when we talk about units, when we talk about sound, and we talk about loudness, we don't really have a unit for loudness. You might say, well, yeah, but like my speaker has like 100 and like it has, or you might have 10, might go up to 12. Sometimes, sometimes you can actually turn it up, your speaker up to 11. There's actually a joke about that but I can't remember the film actually. But yeah, there are, even though they've got these values, they don't actually compare. So if you turn your phone up to like 13, but then you turn your speaker up to 12, your speaker is going to be a lot louder than your mobile phone is, even though they're the same number. And if you turn your car speaker up to 23, that might be like even louder than both of them combined. So we need to get some units, some consistent units that we can use in physics, so we can say, right, okay, this speaker, even though it says it's producing a volume of 12, what does that actually mean? How do we actually compare them? Before we get too deep into loudness, let's talk about what we discussed last lesson. Last lesson we were breaking down the movement of sound, because we spent all of the lesson before that talking about waves. So it was made sense to talk about, well, okay, how do these waves actually move? We said that these waves move because of particles. We said that as particles crash into each other, they push other particles forward, which allows for a sound wave to move forward, but they also push against each other and push each other back, which allows for a sound wave to fill up the area that was missing. But this part, and because it's a sound waves are caused by particles, it makes sense that if you've got something that's more densely packed, like steel, it's going to have a lot faster speed of sound than water, because also and water is going to have faster than air. And of course, if you have a vacuum, then the speed of sound would be, 0, because there would be no particles at all to move through. We also talked about a sonic boom. That happens when you have an object moving faster than the speed of sound. That's just not actually part of the course per se, but it's just something that I thought I'd throw in there, just so that you know what a sonic boom is. It's moving faster than the speed of sound, so therefore it's breaks the sound barrier, and as it produces sound, the sound can't keep up with it, so it makes this sonic boom. I believe the sonic boom is because all of the sound waves are produced so close together, and so they all the particles just get pushed left, right, and center, and it goes ballistic. I actually don't understand enough about sonic booms to really properly teach you guys about it, but I do know that it's related. We talked about how sound waves have areas of high pressure and areas of low pressure. And if you use those areas of high pressure and low pressure, you can actually graph them. And then once we've got a graph, we can start doing some things. We can start doing some analysis. We know that the graph is made up of high points and low points. The high points we're going to call compression. The low points we're going to call rarefication. You know what? I actually think it makes more sense to put this slide before the other one, but doesn't matter too much. So yeah, we then looked at the sound wave in a bit more depth, and we said, well, we're going to look at the sound wave just like how you would look at a regular wave. You've got Just like you look for a light wave or whatever, you've got an amplitude and you've got, or a radio wave. You've got here an amplitude and a wavelength. An amplitude being how high the wave gets, and then the amplitude, and that would be the coefficient in front of sine, by the way, if you're someone that's paying attention to methods. And the wavelength is the distance between the two things. It's very similar to, and the period, of course, is also, the period and frequency is also what we talked about. We talked about frequency being, then we did a quick comparison between period and frequency, and how to convert between them, because frequency is how often a particular sound is going through a point. How many times can I click in a second? Whereas a period is how long does it take for one wave to go through. So they're pretty much the inverse of each other. They're the same value, is just flipped upside down. So because of that, we can actually use that. Frequency as well can be used when we talk about sound as the difference. High-pitched sound, like a squeaky voice, when you inhale helium, that's going to be a higher frequency. Whereas a lower frequency is linked to pitch, is like a lower, deeper sound. And it's linked to this idea called pitch. Pitch is actually a musical concept, and it's something that we're going to talk about more and more later on. But yeah, so we then looked at this formula, these two formulas for calculating speed of sound. So that's two different formulas that are really, really important. And then we gave a bit of a practice of those with some figuring out how long a sound wave would be if it was 262 hertz. Then what we did was we actually compared it. We actually looked at what that would look like. We looked at, here is 262 hertz. And so, yeah, we explored how long that would be. And then we looked at all these other frequencies and how long they were. And then we finished up by talking about diffraction. Diffraction is actually, again, still linked to sound waves moving. It's talking about how a sound wave would move around an object. And of course, the trick here is longer, deeper sounds are able to bend more than high-pitched sounds. And so therefore, that's why you can hear the rumble of cars, the deep rumble of cars from, you know, a classroom that's nowhere near Ballarat Road, but you can't hear the honking of horns or anything as well, or as clearly. And that's because the deeper sounds can bend around walls and so on. This is an example. Shush! This is an example of the sound waves bending. Now, sorry, doggy decided to bark. Okay, so question, hopefully, maybe. Why do longer waves bend more? A good question. Why do longer waves bend more? I think it's because higher pitched sounds get absorbed more easily. It's also got to do with the fact that because they're longer, I think it's like they can, whereas shorter waves like small packets, whereas longer waves can sort of just stretch around. I actually don't really necessarily know 100% why they do. It might also have to do with their energy. Longer waves have less energy, but I'm not actually 100% sure why. I just do know that longer waves bend more than shorter waves. Something I should really look up, to be honest with you. So let's start talking about loudness. Or by all means, though, if you want to look it up yourself, you can look it up yourself. I mean, like if you, because I don't have to be your sole place to get knowledge. So let's go have a look at loudness. Now, loudness is the first thing we're going to talk about with loudness, is how it links to our waves. We've talked about how frequency can be explained between high pitch and low pitch. Loudness appears to is how loud a sound appears to be is based off the amplitude of the sound wave. High amplitude waves are going to result in a louder sound. whereas a lower amplitude wave is going to result in a lower, quieter sound. That one should hopefully be a little bit obvious to you. If you've got a louder sound wave, if you've got a higher amplitude, that means you've got higher areas of high pressure and lower areas of low pressure. And so that's going to be pretty important to understanding how loudness works. You don't need the picture here, like it's not essential that you have this picture here, but it's just another way that I can link back. And what I'm trying to do here for you guys is to constantly keep linking back this idea of this is the physics, like this is the physics, this is the understanding of the wave versus this is how it relates to real life. High frequency, what does that look like on a wave? What would that sound like to your ear? Quiet versus loud, what does that look like as a wave compared to what does that look like as your ear? Obviously, I'm trying to avoid that because I keep saying, what does that look like to your ear? That doesn't make sense at all because you can't see something with your ear. Okay, dampening sound. Now, obviously, one of the problems with sound, though, is that the amplitude is not going to be constant. And that's something that's very, very true. Obviously, even though if you make a sound, you guys very, very clearly know from probably many experiences that if you make a sound, that as that sound gets further and further from you, it's going to get quieter and quieter. If you are speaking to your friend who's standing right next to you, you don't have to worry about the person on the other side of the room being able to hear you, because by the time the sound waves from your mouth get to that side of the room, they're probably very, very quiet. Now, there are lots of reasons why that's the case. The main reason is that as that sound wave goes from your mouth on one side of the room to the other side of the room, it needs to spread out. So even though it hasn't spread out very much by the time it gets to your friends so they can hear it, but by the time it gets all the way out to the other side of the room, it's going to be pretty spread out. So in order for you to make sure, if you want the person on the other side of the room to hear you, you have to speak louder. You have to start off with an even higher amplitude so that by the time it gets to your friend, they can still hear him. The other reason why, of course, and this is sort of the answer to B as well, answering to A, is that energy is lost. We all know that energy gets lost in some ways and forms because we talked about efficiency earlier on in the year. Earlier on in the year, we talked about that in the last topic. So we know that some of the energy is going to get lost. And so, of course, that's true. You have to move a large amount of air. So some of that air might vibrate the wrong way. And so therefore it might cause a small amount of heat. And so therefore that energy is lost. And so that energy doesn't go to moving that wave forward. And so essentially that energy will disappear over time. So that's sort of why something gets quieter as you get further and further away from it. But the main one is, yeah, it's spread out over a larger area. Now, this is actually going to be the main focus that we're going to be talking about today, is how does this work? How does something get quieter or louder, and how can we measure the loudness of something compared to the distance from it? For those of you that are really mathematical here, the main thing that we're going to try to do is we're going to try to figure out how does this curve here change? How does this curve, the curve, not the sine curve, but the curve that's lowering it. For those of you that again are doing methods, I would like to point out, I'm not sure if you guys have ever done like multiplying functions. Actually, that might be more of a specialist math thing. Just a quick thing. What you would do is you take f of x, you take g of x, which are two different functions, and you multiply those functions together. This is an example of why it's important to be able to multiply different functions together. Because when you multiply these functions together, you get a you can get something like a decaying sine curve. I think that if you multiplied something like, I don't know, sine of x and maybe what would be, that would be e to the negative x maybe. But yeah, I'm not teaching you specialist maths here. I'm just trying to explain to you guys, you know, the basics here, which is essentially as shush. Sorry, as you get further away from the source, it's going to get quieter. Now, let's move on to this idea here. And I say this idea here, but let's be honest here, this is not a new idea. This is I wanted to reintroduce you for the third time to the idea of power. Now I say the third time because the first time I taught you about power was in lesson 26. And the second time I taught you about power was lesson 77. And now what is this? Lesson 80 or something like 84 or something like this, where it's looking at it again. Just for the record, power, and this power, in this case, we're going to be talking about power. We're going to be talking about acoustic power because we're going to be talking about sound is a measure of the energy per time. It's measured in watts and it's energy per time. If you don't remember this from either of those two lessons, this is the quick revision here. So we're going to use this idea of power because ultimately when we look at something like a speaker, like a drum, like a hammer hitting a nail, we're looking at an energy over a certain time, and that's going to produce a sound wave, and that sound wave is going to carry energy with it. And the energy that it carries is going to be dependent on how long it takes for that energy to move. So we're going to be talking about power. I'm not going to keep this slide up for very long because we've seen this slide twice before. But I want to talk to you guys about something new with power. What we're going to move on to is we're going to look at a different way that we can use power. We're going to look at something called intensity. Now, intensity is a new topic. Intensity is a measure of the amount of power over an area. Its formula is I equals the intensity equals P over A. Now, you have to be very careful here because I is the same unit that we use for current. So be careful, even though we're using the same letter, to, you know, be aware what type of formula you're using here. Now, the units of this are watts per meter squared, which kind of makes sense. Power is measured in watts, area is measured in meters squared, so intensity is watts per meter squared. Pretty explanatory in my opinion. Now, intensity can be used to describe light or sound or anything where energy is spread out over an area or a volume. More area than volume because obviously it's area, but still the idea is as sound spreads out, its intensity goes down. As light spreads out, its intensity goes down. If you shine a light near the source, its intensity is very, very high. But further away, its intensity goes down, and that's because it's over a larger area. if you try to use light to if you try to use just a torch to light up a whole soccer pitch, you wouldn't have very much luck because it's a large area. You would need to have a high power torch in order to light up a whole soccer pitch. Same with if you had a soccer pitch and you were the announcer and you're trying to announce the scores, you would need to have a very powerful loudspeaker to spread it out, to spread that out so that everyone can hear. Because ultimately you want everyone to have the same intensity. You want everyone to be able to hear the same sound. The closer, and intensity is just a measure of how spread out that, how much energy you're going to get after it's been spread out over that area. Does that make sense? Do you guys understand what this idea of intensity is? A yes in chat. I'd appreciate yeah, that makes sense in chat. Or maybe yeah, if it doesn't, if you don't get it, that's fine. I can go back over it. Yeah, okay. Someone seems to get it. Yeah, if you intensity is so, and of course you guys just sort of have a general idea of intensity anyway. You guys sort of know if something's intense, you're like, oh man, that was really hard to do. That was like a lot going on. So if something's intense, it's like really lots of stuff hitting you. You hear if you were someone to say, wow, that sound is intense, that would mean that there is a lot of sound hitting you. Whereas if you've got low intensity, that means it's going to have not much. So let's move on from intensity to start to bring this idea back to sound. So we're going to do that by looking at this idea here. Oh, actually, before we do that, we're going to look at an example. Sorry, we're going to work on this example here. Sorry about this, ladies and gents. The units in this have sort of like the units haven't worked out very well. So let's grab a look here. A window has an area of 0.50 meters squared. That M2 means meters squared. So we're going to write that down, 0.05 meters squared. 4.5 times 10 to the power of -4, that's what that -4 means. Joules of energy passes through the window in 30 seconds. Calculate the acoustic power of the sound intensity at the window. Okay, so let's calculate the acoustic power. Power equals energy over time. Okay, so power equals energy over time. We have 4.5 times 10 to the power of -4 happening over 30 seconds. Okay, because that's our time. So that means we've got 4.5 times 10 to the -4 divided by 30 equals 1.5 times 10 to the -5. And the units of power are watts. Beautiful. All right, ladies and gents, I would like you guys to calculate the intensity, remembering that intensity is power over the area. I'd like you guys to quickly calculate that. You can use your calculator, you can use your phone, you can use your computer to do it. I don't care. I'm not going to move on from this slide until I've got at least 3 answers in chat for what the intensity would be. And I'd like you guys to try to include the units as well. So I'm not going to give you guys the answer until I've got 3 answers in chat. What is the intensity of the sound? Question B. Okay, I've got one answer. I got two answers that are very different. Interesting. I'm looking for one more. And I've got one more. Okay, beautiful. That's three. Let's do this together then. I'm also going to write down the names here of the people that actually contributed because, you know, thanks. Ooh, cool. Okay. That's a third different answer because I'm going to later on in this lesson, I'm going to maybe in the next 5 minutes, I'm going to ask maybe someone else to input. So we'll see how that goes. So let's, and someone correcting themselves. So let's go have a look here. B, this intensity equals power over the area. The power in this case is 1.5 times 10 to the negative 5. The area is 0.05 because it told us that that's the area in meters squared. So that means that if I take my 1.5 times 10 to the negative 5 and I divide it by 0.05, that's going to give me 3 times 10 to the negative 4 watts per meter squared. Now, I imagine that some people may have gotten, so some people here I've seen have gotten 9, and I assume what they've done is they've thought, oh, maybe they've gone 0.5 times 0.5 to get to this area per square. But you have to realize here, they've actually, you're working too hard. You're working, sorry, 0.05. You're working too hard for your money because they've already given you the area. It's 0.05 meters squared. You don't need to recalculate that again. If I had have told you the length of the window is 0.5 and the width of the window is 0.05, calculate the area of the window, then yeah, sure, that's what you would do. Right, so that's how we can calculate the pressure over the intensity over through a window. But here's the thing, right? The problem that we've got with this example, although it is a good example here, is that it's not it doesn't really take into account the issue with the issue is that sound rarely just goes through a window. How does sound look in just real life? What does sound look like in real life? And that's where I wanted to introduce you to this idea here. Sound in real life, if you imagine a point source. Now, when we say a point source, we mean a single point. Imagine that just you've got this tiny 1 millimeter by 1 millimeter point that's making sound. What we could do is you could imagine that the sound coming from that point and emitting the sound wave, and the wave will go out from that point as a sphere. Now, that seems to make logical sense to me, and especially because if you've watched enough, as I've said before, anime sort of shows, you know that all the shock waves go out as a sphere around the object. And that's essentially what's happening. If you grab a look inside this cube here, you can see that the waves are going out from the tuning fork, which is what I believe this is supposed to be, in the form of a sphere. And they go further and further out. Now, the advantage for us is that we actually, and the same with this gunshot here, this is making sound waves that are going out in the form of a sphere. The advantage for us is that we actually have a way that we can calculate the surface area of a sphere. The surface area of a sphere is equal to 4 pi r squared. If you don't believe me, you can look that up yourself and find it out. But yeah, it's 4 pi r squared. So that means we can change the intensity formula. So instead of being I equals P over A, we can replace the A with the surface area of a sphere. I equals P over 4 pi r squared. That 4 pi r squared is because that's the area that's going to be, that's the area of the sphere that the sound is going to be produced. Now, obviously, we're going to have to be, obviously there are some extra little caveats here that I want you guys to be aware of. Obviously, in real life, that you're going to have other issues in that you're going to have sound reflecting off walls, off the ground, off other things and stuff. So sound isn't going to come out of an object as a sphere, but for a general understanding, we're going to assume that sound comes away from a sphere. And that gives us this formula, I equals P over 4 pi r squared. Okay. And we call this the inverse square law, and there is a reason why we call this the inverse square law. The reason we call this the inverse square law is because it's got this idea of r squared. And I'm going to probably finish up today by talking about what the inverse square law is. Oh, actually, no, I'm not. I'm gonna, you know what? I've only got 3 minutes left. I'm going to talk about the inverse square law. I'm going to talk about the inverse square law on Friday instead. But what I will talk about today is we're going to do one quick example with a sound wave. So let's go have a look at this quick example here. The sound of a passing car from 8 meters is measured to be 1.8 times 10 to the negative 4 watts per meter squared. Assuming the sound acts as a point source and ignoring the effects of reflection and absorption, what is the total acoustic power of the car? So we're actually looking for the total acoustic power. We're looking for P. We've been given this, which is I, and we actually have been given 8, which is going to be our R. So we're going to use, thank you, all of these measurements, because what we're going to try and do is going to go intensity equals power over 4 pi r squared. Now, if we know that we want to work out the power, so that means the intensity times, and we're going to multiply both sides by 4 pi r squared, times 4 pi r squared gives us our power. So the intensity was 1.8 times 10 to the negative 4 watts per meter squared. We just have to work out how many meters squared are in this 8 meter sphere. So the 8 meter sphere is going to have times 4 times pi times 8 squared. That's going to give us our P, or our power. I'm going to quickly do this in my calculator because I know that we're pretty much at the end of the lesson here. 1.8 times 10 to the negative 4 times 4 times pi times 64, because 8 eighths is 64, gives us 0.1, let's 0.145 watts. So about 100 milliwatts. So that's actually not that powerful. But then again, of course, you don't want it to be super powerful. The picture here on the right is, of course, apparently you can attach massive exhausts to your car to make it super loud, which is stupid, but okay. But yeah, that's how you would could work out the total acoustic power of a car. Ladies and gents, we're going to talk more about this formula, this intensity formula, how it can be sort of like generalized on Friday. And also we're going to talk about decibels. So yeah, bring a calculator on Friday because you're going to need it, because we're going to start to talk about decibels, which require logs and log laws. If you're doing chemistry, then you're probably pretty comfortable with logs already from all your work on pH. But yeah, we're going to be working on that next lesson. That's the end of the lesson, ladies and gents. Thank you so much for listening. I'm going to end it here.